we're going to now take a look at the idea of the remainder estimate for the integral test. This is actually a pretty slick thing that's going on here, because what it does is it allows us to figure out what our error is going to be if we use a partial sum for an infinite series. And even more cool than that is if we say, hey, look, I don't know what this thing really sums up to, but I need to know within 0.01 or 0.000001, we can actually figure out how far out we need to go so that we know our error will be no bigger than whatever it is that we specify. Now, we may never actually know what the thing actually sums to, but we can get a pretty darn good estimate of it. So let's suppose f is continuous positive decreasing for x greater than or equal to 1. And I'm going to let ak equal f of k, where k is 1, 2, 3, so forth, etc. And I'm going to let s be the partial sum. I should have actually said sn there. K equals 1 to n of ak. Actually, that's a typo. This should be k equals 1 to infinity. There we go. That makes more sense. This is a convergent series. And Sn equals the partial sum, k equals 1 to n of ak. Now, I'm going to define Rn as being equal to S minus Sn. So S is what this thing truly converges to. We don't know what it is, but we know that it converges, so we can call it S. Now, Sn is going to be my partial sum. So the difference between whatever it really converges to minus how far we go, that difference is going to be our remainder. Now, the integral of n plus 1 to infinity of f of x dx is actually going to be less than or equal to this remainder, which is less than or equal to the integral of n from n to infinity of f of x dx. And you can refer to your book for a little bit more proof on this, but this should actually seem kind of reasonable just based on the idea of the integral test to begin with. So what this does is, this is a cool part right here, because this gives me a means of being able to figure out what my maximum error will be, or I can set my maximum error and figure out how far I need to go out. So as an example, suppose I need to find the sum n equals 1 to infinity of 1 over n cubed accurate to within 0.01. Okay, so what I want to do is I want to take the integral from n to infinity of 1 over x cubed dx. Now what I'm going to do when I'm done with this is going to be a function of n. And I know it's going to be a function of n. It's not going to blow up because to begin with, we had to have that 1 over x cubed is convergent to begin with. So maybe just a straight integral test, if you weren't sure, from 1 to infinity would have confirmed that this thing really is convergent. So now I'm trying to figure out what it converges to. So if I integrate this now, again, an improper integral, so I need to take a look at the limit as b goes to infinity of the integral from 1 to b. I'm going to write this as x to negative 3 dx, is simply because it's set up nicely to go ahead and take our antiderivative. This is going to be equal to the limit as b goes to infinity of, and I'm going to end up when I take this antiderivative as negative x to negative 2 over 2. I need to evaluate this from 1 to b. Now I'm going to rewrite this as the limit as b goes to infinity, just so you can see what's going on a little bit easier, of 1 over 2x squared evaluated from 1 to b. See, it's the same thing. And this is going to be equal to, oops, I messed up. I've been doing ones here. This is an n. Right there, an n. I'm thinking the integral test. This is closely related to the integral test, but it's not the same thing. Okay, good. I just fixed that. Hope you weren't freaking out too much. So this could be equal to the limit as b goes to infinity of negative 1 over 2 times b squared minus negative 1 over 2 times n squared. Well, in the limit, this goes to 0. This double negative is a positive. So what I end up is 1 over 2n squared. Cool. But what do I do with it? Well, what I need, remember this is a remainder. This is Rn is going to be less than or equal to this. So if I stop at n, I don't know what n is yet, that how far I'm going to be off is going to be no more than this integral. Okay, if I put in a value for n, I can figure out what this value actually is. But I said I want to be less than 0.01. So what I need is 0.01 0.01 to be less than equal to 1 over 2n squared. Okay, so that would then imply, oops, actually I should turn this around. I'm going to turn this around real quick. I'm going to look at it this way. I want this to be less than 0.001. So what I need is 1 over 2n squared to be less than 0.001. Oops, 0.1. Not having a good day today, am I? That's all right. We're okay. There we go. That's a 0. All right, that would imply that, because I want my remainder to be less than this thing. So that would imply that 1 over 2 times 0.01 must be less than or equal to n squared, which implies that the square root of 1 over 0.02 must be less than or equal to n. And then at this point, I think I would probably reach for my calculator to figure out what the square root of that thing is. And what you're going to end up with is approximately 7.0711 must be less than or equal to n. So I would say let n equal 8. So what I'm convinced of now, or I can say now, therefore, the sum n equals 1 to 8 of 1 over n cubed, whatever that is, I can sum that thing up, whatever that is actually within 0.01 of the sum n equals 1 to infinity of 1 over n cubed. Okay, so I'm going to jump into Maple here, and I'm going to let Maple add this up for me because it's a lot faster than I can with my calculator in my hand. So I'm going to tell Maple to do the sum of 1 over n cubed, and I want n to go from 1 to 8. And it's going to give me a number. Great. I think I want something I can understand a little bit better, so I'm going to tell it to evaluate floating point, that last value, and that's about 1.195. Okay, so now I'm going to cheat. I'm going to just copy this thing over. So I'm going to copy it and paste. And I'm going to get rid of this 8. I'm going to make this 8 infinity. Now let's see if Maple can go to infinity. Just thinking about it. Oh, it's the infamous zeta function. It's zeta of 3. Okay, that was pretty useless to us. And the reason I say it was useless to us is because this zeta function, zeta of 3, what the zeta function is actually a p-series. This is saying that this is actually equal to the sum n equals 1 to infinity of 1 over n cubed. Well, yeah, no kidding, that's what I asked for. So Maple just gave me back exactly what I gave it. But I can tell Maple to do a good approximation for me, and I can tell to evaluate floating point of the last one, and it's going to go out there a long ways out there, and it's going to tell me that it is 1.202. Now notice that if I add 0.01 to this, I am within, that would be bigger than this, so I am in fact within that margin of error that I said that I wanted to be. And I just told Maple to do that for me, so I took this last value right there and I subtracted it from this sum. I just copied this, and then bam, I am definitely less within 0.01. I'm within 0.0068. So it worked.